All right, today we're diving into one of the biggest, most ambitious quests humanity has ever taken on, trying to build a star right here on Earth. It's a mission that's been going on for decades, and you know what? If we pull it off, it could literally change everything about our world.
I mean, just think about this for a second. What if we could tap into the very same energy source that makes the sun and all the stars shine? Clean, safe, and practically limitless power. That's the incredible promise of nuclear fusion. So let's break down what that really means.
Okay, first things first. To really get why this is such a monumental challenge, we have to understand the prize we're chasing. We're talking about unlocking the very process that powers the stars.
At its heart, fusion is basically the opposite of the nuclear power we have today. You see, instead of splitting heavy atoms apart, which is fission, fusion is all about taking really light atoms, like different versions of hydrogen, and smashing them together so they combine. When they do, a tiny bit of their mass just vanishes. And that lost mass, it turns into a colossal amount of energy. It's the engine that runs the entire universe.
And this is where the benefits just become so obvious. Look at this comparison. On the right, you've got fission. That's what our current nuclear plants do. They split heavy stuff like uranium, which is in limited supply, and it creates that long-term radioactive waste we're always worried about. But fusion, on the left, is a whole different ballgame. The fuel is abundant. One of its key ingredients, deuterium, can be filtered right out of seawater. And the best part? It's inherently safe. There's no chain reaction. A meltdown is physically impossible. If something goes wrong, the whole reaction just stops.
So you're probably thinking, if it's that good, why don't we have fusion power plants everywhere? Well, here's the catch. It is mind-bogglingly difficult to do. Trying to recreate the conditions inside the core of a star is, without a doubt, one of the toughest engineering puzzles we have ever faced.
Success all comes down to hitting 3 critical targets at the exact same time. It's something scientists call the triple product. First, you need insane temperatures to get the atoms moving fast enough to fuse. Second, you need to cram them together densely enough so they actually collide. And third, you need to hold them in that state long enough for the fusion to actually happen. It's like a 3-legged stool. If you're short on any one of those, the whole thing falls apart, and your mini-star just fizzles out.
And when we talk about temperature, we're talking about numbers that are just astronomical. We need to get the fuel hotter than 100 million Kelvin. Let me put that in perspective for you. That is more than 6 times hotter than the core of our own sun. Now, obviously, no material on Earth can handle that. It would instantly vaporize. So that creates this incredible problem. How in the world do you hold something that hot?
So, how do you contain a miniature sun? Well, since a physical box would just disappear in a puff of smoke, scientists had to get really clever. They've come up with 2 amazing ways to hold this super hot fuel without it ever touching the sides of a container.
And those 2 main paths are magnetic confinement and inertial confinement. Think of it like this. On one hand, magnetic confinement is all about building an invisible bottle. It uses these unbelievably powerful magnetic fields to trap the hot fuel, which is in a state of matter called plasma, and just holds it there floating in the middle of a vacuum. The other approach, inertial confinement, is completely different. It's more of a quick, violent squeeze. It uses a massive burst of energy, usually from some of the world's biggest lasers, to crush a tiny pellet of fuel so fast and so hard that it fuses before it even has a chance to blow itself apart.
Now, if we look closer at the magnetic bottle idea, the design that's gotten the most attention and funding is the tokamak. That's that classic donut shape you've probably seen pictures of. It's the design behind ITER, that enormous international project in France. But you know, it's not the only horse in the race. There are other cool ideas like the incredibly complex twisted stellarator, and even smaller, more apple-shaped, spherical tokamaks that are pushing the science forward too.
The squeeze side of things is just as brilliant. At the National Ignition Facility, for instance, they use what's called an indirect drive. Get this, they have 192 giant lasers that all fire simultaneously at a tiny gold can. This creates a perfect, uniform bath of X-rays inside the can, which then crushes the fuel pellet at the center with incredible precision. And there are other methods too, like just blasting the pellet directly with lasers, or using a massive jolt of electricity like they do at the Z machine.
Now, for most of its history, fusion research was this slow, steady, government-funded marathon. But recently, something has changed. The whole field has picked up speed dramatically. We've really entered a new era, one full of breakthroughs, and it's not just the big public labs anymore. There's a huge surge of private companies jumping in, and it's turned into a full-blown race to get fusion power on the grid.
And you can see this acceleration really clearly when you look at the big milestones. Yeah, the JT tokamak in the UK showed big power was possible way back in '97, But the real game changer, the moment that shifted everything, was in late 2022. For the very first time, the National Ignition Facility achieved what's called scientific net energy gain. They got more energy out of the fusion reaction than the laser energy they put in. That was it. That was the proof of concept the world had been waiting for.
And that scientific proof? It was like a starting gun for the private sector. All of a sudden, this wasn't just a government science project anymore. You've got companies like Commonwealth Fusion Systems, which spun out of MIT, using new magnet technology to build smaller, more powerful tokamaks. And then there are companies like Helion that are trying completely different methods. Together, they've raised billions of dollars. Serious investors are now on board because new technologies are finally making a commercial power plant seem like it's within reach. So now it's a sprint, with dozens of companies racing alongside the big national projects.
So, this is the crucial takeaway. We've proven the basic physics works. The question is no longer, can we do it? The question has shifted. It's now a problem of engineering, of material science, and of course, of economics. So what does that road ahead actually look like? And before we get into the challenges, it's worth just taking a second to remember the prize. Why are we pouring all this money and brainpower into this? Well, the payoff is an energy source with fuel that will last for millions of years. It's completely safe, no meltdowns possible, it produces zero carbon emissions and almost no long-term waste, and the amount of energy you get from a tiny bit of fuel is just astounding. This is pretty much the definition of the perfect energy source.
But let's be realistic. The path from a lab experiment to a power plant that can light up your city is still filled with some massive hurdles. For one, we need to invent new materials that can survive being bombarded by high-energy particles for years and not fall apart. Another big one of the key fuels, tritium, is super rare, so a power plant is going to have to make its own. Then we have to get from that scientific gain to engineering break-even, where the whole plant, all its systems included, actually produces more power than it uses. And finally, you have to do all of that at a cost that can actually compete with solar and wind, which are getting cheaper every year.
Which brings us to that old joke that's been around the physics community for decades. Fusion is 30 years away, and it always will be. But when you look at where we are now, we've achieved scientific ignition, there are billions in private money pouring in, there are dozens of companies actually building real pilot plants. The question feels more real and more urgent than ever. Is this time finally different?